Okay, for this problem, we are trying to find the area below a certain point. So let's read the problem. A set of middle school student heights are normally distributed with a mean of 150 centimeters and a standard deviation of 27 centimeters. Darnell is a middle school student with a height of 161.4 centimeters. So basically, normally distributed means that you have a distribution, you have a whole bunch of data points, and they are literally symmetrical. So they kind of make a kind of like a parabola. It looks like a parabola. It's like an upside down parabola, and it looks normally distributed. So basically, my objective here is two goals here: to visualize this and to also actually solve the problem and find the area below that specific point, which is Darnell's height. Mean of 150 centimeters means that all the students average 150 centimeters in height, and they each deviate, and each data point deviates around 20 centimeters from the mean of 150 centimeters. So I'll start with from SciPy, import stats. So basically what I'm doing right now is I'm importing some libraries. So libraries are basically just libraries of pre-written functions that you can use, that you can call and use to your own as you please, basically. I am importing SciPy because that's what we're going to do to calculate the proportions, NumPy because that's what we're going to do to get our x values, and Matplotlib, that's how we're going to visualize and make our graph. I'm doing as PLT because I'm not going to want to write matplotlib.pyplot 5,000 times. Instead, I'll just do PLT dot blah blah blah, whatever function I want to use from that library. So first of all, I'm going to do np dot linspace. So linspace is a function that basically creates an array for you. You can think of an array as a list, but it's a little bit more complicated than that. It starts from a certain point and ends at another point, and then it takes however many points in between that you want it to have. So in other words, if we talk about a mean of 150 centimeters and standard deviation of 20, then maybe we want to start with 100 and then at 200 and then have like 1,000 values in between. And if you run that, Linspace. Okay, spelled that wrong. So if you run that, you're gonna see that it's gonna start at 100, like I said, and it's going to end at 100. So these are going to be at 200, excuse me, and they're going to be 1,000 values in between, as you can see. If you change it to 10 values, then you're just going to have 10 values between 100 and 200. But we're going to leave it as 1,000, and we're going to set that as our x values, because again, remember, we're actually creating this normal distribution. Our y values are actually going to be equal to stats.norm. So we're using norm, which is a function from the stats library, and we're going to do norm.pdf because we're trying to calculate the probability density of each of these x values, but we want to do it in respects with the mean and the standard deviation that they have. So the mean in this case is loc. Loc is what stands for mean, and the mean is 150 centimeters. And then scale is what stands for standard deviation, which is 20, sorry. Scale. So my tip for you is, if you forget what scale and loc is, like which one is which one's mean, which one's standard deviation, just know that scale starts with S, so standard deviation starts with S, so scale, standard deviation are the same, and then whichever's left is going to be your mean, which is your loc. Okay, and that's pretty much it. Now you want to do plt dot plot, so you're getting the plot function from Matplotlib library, and the plot function basically plots a graph for you. So I'm going to plot my x values and my y values, and I'm just going to run that, and you're going to see a normal distribution. So as I said, it's kind of like an upside down parabola. The lines go from infinity, they never actually touch the x-axis, and you can see that the mean is right about in the middle, right? The mean is always in the middle, so it's 150, and they deviate like 20 centimeters each. So like you have 60, then you have 80, then you have 200, so they're deviating 20 centimeters in the x-axis. And again, you have values starting from 100, and you have the values ending at 200, meaning, and then you have basically 1,000 values in between. If I change it to 10, then it's going to be less normally distributed, or less formed, because we only calculated 10 densities, because we only have 10 numbers in between 100 and 200. But that's why we want to do 1,000, because the more, it's called a large counts law, I think, the more samples you have, or the more data points you have, the more normally distributed it will look, even if, whatever. Anyway, too much talking. So PLT dot, I'm going to give it a title, and I'm going to give it a normal distribution with, let me get my mu symbol. I should just literally have these in a post-it note because I always am using them and I have to Google them. Mu equal to 150, and sigma, which is our standard deviation, is equal to 20. So then that's gonna pop up there. And then I'm gonna give it an X label, and the X label is referring to student heights. Student heights in centimeters. And then PLT.Y label is basically the density, right? But that's not what we're going to get to this point. So basically this is our graph. So let me save it and let me explain to you what we're trying to look at. I'm going to call this norm dist to lower and save it in documents. Save. Thank you. Let me open this up. So let me add the image, my device. Is this the one? Yes. Okay. So let me lock it. Okay, so basically what they're asking for is they're asking about the proportion of students' heights, or of students whose height is lower than Darnell's height. And Darnell's height is 161. So 161 is about right here. So I'm just gonna write that line here. So basically what they want is they want this area right here, the area under this curve. This is what they want. That represents the proportion of students who have a height that is lower than 161.4, which is Darnell's height. So where am I? Okay, yeah. So basically, how do you figure this out? Well, there is a function called Normalcdf in your TI-84 or your TI-83 calculator, and I'll show you how to do it with Python too. But real quick, just in case, Normalcdf, basically, you get this by going to second, vars, and then 2, and then it's going to give you a few options. So it's going to give you lower, upper, mu, which stands for your mean, sigma, which stands for your standard deviation, and then it's going to give you, there's going to be a paste option that when you hover over it, it's going to turn black, and then you just click enter. Once you put your values in, it's going to give you your p-value, not your p-value, oh my god, your proportion. So your lower basically is going to be the point that you start at. The point that you start at from left to right. So if you know that you want the proportion, right, the area, or the proportion of all students who have a height that's lower than Darnell's height of 161, then you know that because this is a normal distribution, it's never going to end, and so therefore this goes on until infinity, to negative infinity. And because there's not a negative infinity symbol in your calculator, you want to use a big number like negative 1e99. Some people do like negative 9999 or whatever, but I do negative 1e99 because I feel like that represents it better. So we start at negative 1e99, so negative infinity, and we end at 161.4 because that is the proportion of students, right, who have a lower height than Darnell, right? And then we also have to do this in respects with the mean and standard deviation. So we have a mean of 150 centimeters, but you don't have to put that in the calculator, and a standard deviation of 20. And when you click paste, it's going to turn black. You just click enter, and it's going to give you your proportion, right? And I'll show you how to get that proportion in Python as well. But yeah, that's basically your answer. So whatever you get is the proportion of students who have a height that's lower than Darnell's height. But in Python, the way that you do this, let me show you real quick, is you use this function called, well, it's still the same thing, it's Normalcdf, but you get it from statsnorm.cdf. So again, it's the same thing as saying Normalcdf, and inside, here's the difference. you can only put in you can only put 3 parameters. Your value, which is whatever point you have. In this case, it's Darnold's height, which is 161.4. And then you can only put your which is your mean. So that's 150. And then your scale, which is your standard deviation, which is what, 20? So again, did I mention? Yeah, okay. So this right here, it's going to give you the proportion of students whose height is lower than Darnold's height, 164, because CDF function automatically, or actually better yet, let me say it this way, your normal CDF function only calculates the probability of, not the probability, the proportion. Why do I keep saying that? Your normal CDF function, at least in Python, only calculates the proportion of whatever x values there are that is lower than the point that you specify, which is 161.4. So it's only going to calculate the pink area right here. But we're going to see something later. It's kind of like what if the question is like, what if you could want to calculate the area that's greater than, in my last video I spoke about it, but we'll get to that. But for this problem, just know that you're only calculating the area that's less than this point, just in case you had a question, because there's no upper bound or lower bound, there's just the point, and you just have to know that this calculates the area left to it. So basically it would be normal CDF, what is it, lower bound, so -1E99 to 161.4 with a mean of 150 and a scale of 20. This is the same as what I have on the screen over here, stats.norm.cdf 161.4 150 20. That's the same, because it basically calculates, the area from that point to the left, or below or left, right? That's the same. But we'll talk about one where it's higher. Okay, so if you run that, that's your proportion. You want to round it to 4 decimal places. And it should be, what? Oh, it's because I never told it to round. Okay, 4 decimal places, and it should give you that answer. And that is the proportion of students whose height is lower than Darnold's height, which is 161.4. Do I keep? Yeah, Darnold's height. Okay, so that's right. So now let's try to see a problem where we have to calculate, oh, perfect. A problem where we have to calculate the, what do you call it? The proportion above, or the area, or the proportion above, what do you call it? Above or higher than a point. So let me take this. So it's going to be norm dist high problem. I name my images so badly, like it's really bad. Okay, let's go to documents. Okay, let me upload that. Paste that in there. Alright, so again, I'm just going to go through this real quick. From SciPy. Import, why can't I spell? Import what? Stats. Then we're going to import numpy as np, import matplotlib, plotLib.pyplot as plt. Okay, we're going to do np.linspace, set that to, oh, what's the problem? A set of bed prices are normally distributed with a mean of $1,300 and a standard deviation of $300. A wooden bed has a price of $1,399. What proportion of bed prices are higher than the price of the wooden bed? So first of all, let's visualize the distribution, right? So Linspace, we want our x value. So we think of where the mean is, it's 1,300. So we kind of want, let's say, like 1,000 to maybe 1,000. Well, yeah, okay, let's do 1,000, see how that goes, and let's do 1,000 values in between, and let's call those our x values. again, our y values are going to be the same as stats.norm.pdf, and we're going to do the PDF of all our x values. And then we're going to do plt.plot, and I'm going to do my x values and my y values, and we'll see how that looks like. Oops, that is really bad. 1,000 to 2,000, 1,000, 100. What now? 100. What's the mean? 1,300. So what? 1,100 to 1,800. 1,000. Like 10,000, man. I don't know. What's the issue now? Stats.norm.pdf, plt.plot, x values and y values. Y values is equal to stats.norm.pdf, x values. Oh, I forgot to add the location. I mean the mean and the standard deviation. So the mean is 1,399, and the scale is what is it? 300. Okay, that's really bad. So let's go back to our original thing of 1,000. I think we started at 1,000 and ended at 2,000, I think. Ugh, that looks really bad. How about 1,000, 2,000, 500? 500, 1,500? That's really bad. 2,500. There we go. Okay, that's kind of normally distributed. So either way, it doesn't change the fact that the mean is in the middle of the distribution. It's right in the middle. It's at about like 1,399, and each data point deviates 300. What is the dollars from the mean? So to get some context again, I'm actually just gonna go back and copy and paste this because I don't want to write this 5,000 times. Okay, let me take this and then just 1,399. I'm gonna do dollars, and it deviates 20. Is it? No, it's $300. And what's our x value? A set of bed prices are normally distributed. So these are bed prices in dollars, and yeah, density. So and that. And that is our image. So let me save that and then talk to you about basically what this means. So documents, save. Okay. Image, here, my device. Is it this one? I don't know. I can never remember. No, that's not the... That's literally not even, literally get out. What is it? Hi, this one, this one, this one. No, okay, delete this one. Pretty sure that, yeah, okay. Did I not tell it to do the percent sign? Okay, so basically, what is it asking? Let's go to the problem. If we could ever find the problem. Oh, you're kidding me. Okay. Isn't it? Okay, over here. So a set of bed prices are normally distributed. So now you can see how the bed prices are normally distributed, meaning, you know, that they're symmetrical, etc. The mean is about 1,399, which is around here. It's always in the middle, and then each bed price deviates around $300, $300 away from the mean. So they're asking what proportion of bed prices are higher than the price of the wooden bed. The wooden bed is the price of $1,399. So I'm sorry if I confused that with the mean earlier. 1,399 is around like here, kind of over here. So basically what they're asking for is they're asking for the area that is above this point or higher than this point, which is anything over here, right? Because these are in dollars and etc., so they're higher at that point. So this is $1,399. That's the bed price, and they're asking what is the area here? What is the proportion of beds that have a price that is higher than $1,399? So in the other problem, we had to find the area that was below, and we used Normalcdf, and we're still going to use Normalcdf here, but the only difference is, I'm going to show you real quick. So again, if you in your calculator you do second vars 2, that should be your normal CDF. Again, it's going to give you lower, upper, mean, sigma. So in other words, why are you, oh my god, what is this? Okay, lower, upper, mean, sigma. So your lower is going to start at the lowest point, which is 1,399. Your upper is going to be 1E99 because again, you're only looking for the area from here, from 1,399 and upwards. That is the area, that is the proportion of beds whose prices are higher than this, obviously. So, and again, normal distributions, they never end. These distributions, they never end. So it goes on to infinity. And again, because we don't have infinity in our calculator, we use a big number to represent infinity. So 1E99, or you could do 99, 99, 99, whatever. And then your sigma should be 1,000. What was it? 1,000. I messed up. It's supposed to be 1,300. See, I knew I said it somewhere. Okay, this is supposed to be the actual distribution. It doesn't matter. We're still going to get the right answer. This is 1,300. Okay, scale 300. Okay, still same thing. The distributions all look the same thing. The only difference is the numbers in the x-axis, but whatever. Okay, so your mean is, what is it again? 1,300. 1,300, yeah. And then your standard deviation is 300, and then you click on paste, and it should give you an answer. But now that answer is good, right? If you use a TI-84 or TI-83, if you use a calculator, that answer is good because you specified your lower bound, and you specified that you wanted it to calculate the proportion above that point, right? But in Python, you can only put in 3 parameters. So for stats.norm.cdf, which is the same thing as normal.cdf, you can only put 3 parameters. You can only put the point that you're trying to figure out, which is 1,399, and then you're trying to put the log, which is the mean, which is 1,300. Wait, 1,300, yes. And then scale is 300. Here, there's no place to put bounds. It's just the point, because you have to know that CDF calculates the proportion of or the area of actually below a point. So in this case, you're gonna have to do 1 minus that to get the area above a point, because it's the opposite basically. And again, you just want to round to 4 decimal places, round that, and then that should be your answer right here. Okay, but yeah, another way to do this, again, I mentioned in my last video, is to do stats.norm.sf. SF is the same as 1 minus CDF, and just put in your values. So 1,399, log, which is your mean of 1,300, and your scale, which is standard deviation of 300, and it should give you the same answer if you again round it to 4 decimal places, if this thing wants to load ever. See? So that's it. But if you use your calculator, because it lets you specify your lower and upper bound, it's going to do as you say, and it's going to calculate the proportion or the area above or below that point as you specify. But in Python, normal CDF is actually, it calculates the proportion below a point always, and that is known even in the real world. But your calculator just has, it kind of basically has an SF, not really an SF, it just has I think it has another function, and it depending on what you put, it uses either or. But here you have to do it kind of more manually, so you have to use your own intuition and know like which way are you calculating above, or are you calculating below, and depending on that, that's the function you have to use. So if you're calculating above a point, you want to use SF or 1 minus CDF. If you're calculating below a point, you want to use CDF, just CDF, okay? And in Python, but in your calculator, you just specify the parameters that you want the proportion or the area to be found above or below, and I'll give it to you as you ask it. But yeah, that's the answer, and those are the differences between the functions and how to use them in each case. Yeah, okay, bye.